Welcome to the Math Record. Today we'll be covering integral volumes like revolutions. This video will cover part 3 of chapter 3 in our calculus class. Okay, let's begin. So what are integral revolutions? Well, basically, let's have a graph. Let's use like the simplest case. Let's use a line, right? And it goes through the origin. So let's restrict it from the origin to this point right here, right? So we have this area. Okay, the idea of integral revolutions is that we're going to make something, a 2D shape, into a 3D shape. So how do we do this? Well, based on this name, integral revolutions, we have to revolve it around something. And there's technically only 3 ways to revolve it around. We're either going to revolve it around the y-axis, or we're going to revolve it around the x-axis, or we're going to revolve it around a line that's parallel to one of these axes. So it's either like parallel to the y or parallel to the x, right? So generally, the idea for how this works is that we're going to have this 2D to 3D. So if we revolve it around the x-axis, what would that shape look like, right? We have a 2D triangle, and if we revolve it, right, how would that look? Well, basically, it's just going to be a cone, right? Because we're going to have a triangle, right? And we're going to have our x-axis. We put a point right here, right? So it's this point is equal to this orange point right here. And we're going to revolve a triangle, basically, around like the x-axis. And then that triangle would technically just get like a section of our cone and just revolve it around. It might be really confusing to understand, but we have an x-axis and a y-axis. Now imagine we had a z-axis, right? So it's a 3-dimensional graph. And then we need to revolve it around, right? In the 3rd dimension. And then you basically get this shape. So the general idea is that we, for calculus, is that we would like to somehow find a numerical answer for this volume. So how would we do that? Well, basically, what we would do is that we could think about circles. So how this works is that, let's say we just have lines right here, here, and here, right? Now, if we were standing right here, okay, and we were looking into the graph this way, right? So we're not like in our screen, right? Our screen, and we're watching this video, and we're looking through this way. Let's say we're looking at directly at the line, okay? So what will our perspective be? Well, basically, it looks like this, right? We have a point right here. That's our point, and it goes up. So instead of going around this way, like, oops. So instead of going like down here and then going around, right? Then basically it's gonna go this way because you're looking directly at it, right? Because you're looking directly at your graph. Then basically, what would this shape look like? Well, it's really simple. I just drew it for you. It's just gonna be a circle, right? Because if you continually just draw that line around, it's just gonna be a circle. So this line would technically just be a radius, right? So this is our radius. So how would we find the volume based on these circles that we could keep drawing? Well, if we could keep drawing the circles, let's see how that looks in the graph, right? So let's say we have a circle right here, right? I'm sorry if my pictures don't look the best. They're not to scale. And then there's something like right here. And then we have an even bigger one right here, right? So what would this look like if we had to do it infinitely, like if we had to draw infinite amount of lines and we had to do circles for them, right? So if we had to draw a line here, 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 right? You draw infinite amount of lines and you have to make infinite amount of circles, right? What would that look like? Well, if you put all them together, right, we just make a cone. So if you still don't understand how this kind of looks representedly, technically, what you could think about is that we could think about coins, right? So imagine we have like a penny, a dime, which is smaller than a penny. I don't know why. And then we have a nickel, and then we have a quarter, right? So let's put all these circles from smallest to biggest, right? So we have the dime, we have the penny, we have the nickel, and we have the quarter, right? So smallest to biggest. Now, if you put them all close to each other, right, under each other, what does that shape look like? It looks like a cone, right? Generally, we have a general shape of a cone. Now, if you, the only reason it kind of doesn't look like it is because like they're like obviously not a cone because of how the radius are shaped. If the radius were even closer to them and there was more coins between, right? So we have infinite amount of like circles, right? And they're increasing in radius, so their area is increasing. What does this look like now? If we have infinite amount of coins and we just really small and it gets increasingly bigger. Well, it looks like a cone now, right? And that's a general idea about how these areas under the graph work, these revolutions. So if we have infinite amount of lines, right? And we have infinite amount of circles, then these infinite amount of circles, if you put them all together, then we're gonna have an idea of a cone, right? So that's the general idea of how this works. It even works if it's not like an actual line, like a linear line. We could use these with curves. So how this would look like is that let's use like a parabola. Something like let's make this easier to see. So we have something like this, okay? And let's say we want to find the area from the origin to here, okay? Right, the origin to this point. Well, we could just think about circles again. So let's draw a line here, a line here, a line here. It doesn't matter how much lines you put or like where you draw it. I'm just doing this for a visual purpose. So what would this look like in 3D? Well, it doesn't look like a cone anymore, right? But it's really similar to a cone. So what it will look like is that we have like some kind of outline as the parabola, right? And then if you revolve it around, then it kind of just looks the same on the other side. And the outside would just be like a circle, right? So this would be our general shape of how it looks. So it kind of looks like a cone, but not really. A cone is more uniform, right? Oops. Right, you draw a circle. Right? So that's what a cone looks like. It has a straight line. This one is increasingly up, right? Because it's a parabola. So that's the general idea of what it is. It kind of looks like some kind of like hat, like from a witch or something, right? So that's basically how it looks. So based on this idea, you could still technically still use circles. It's just that the circles have different radius, and the radius is increasing at like at a quadratic formula, right? So it's speeding up basically. So it's not gonna be linear, but it's basically still able to use circles. We just had to put infinite amount of them. So how do we find this area under this circle? I mean this volume for under these graphs. Well, basically, there's a really easy formula to do. It's basically just your volume is equal to pi, like 3.1415, etc., right? Just pi. And the integral from x is equal to your first number to x is equal to your next number, your ending bound, basically. Your beginning bound, your ending bound. And then you're going to have your equation, f of x, and you're going to have f of x squared. And then you're going to do this all in respect to dx. And this is your formula. So why is this the formula we use? Well, basically, we're using circles, right? What's the equation for an area of a circle? Well, area of a circle is pi radius squared, right? Sorry. It's just a habit how I write pi. So it's pi radius squared, right? Now, where would these variables be? Well, our pi is right here, and our radius squared is right here, right? Because fx is squared, so that's our radius. Fx is our radius. So why is fx our radius? Well, basically, if you look at our graph, we draw that linear line again, we have fx, right? Fx is technically our height, our radius, per se. So let's actually use like a actual example. Let's say we have f of x is equal to 2x, right? When x is equal to 1, f of 1 is equal to 2, right? You just plug it in. And when x is equal to 2, f of 2 is equal to 4. So let's put that, let's say x of 1 is right here, and x of 2 is right here. So this radius is 2, and this radius is 4, right? Because that's our height. Our height is equal to our radius. So do you see why we have our radius is our f of x now? Because technically our f of x is gonna make our height. So whatever our height is actually gonna become our radius, and that's why this equation works. And then the reason we put this in our integral is that we want infinite amount of radius, right? So we want infinite amount of these circles that we have. And that's the reason why we put it integral, because our radius is not going to stay the same. So the reason we use integrals is that if we want infinite amount of them, basically. So if our radius is basically not the same, then we could use the integral, and this integral will help us calculate for the distances they're changing for the radius, and then we could put all those differences together and basically just solve for the volume through like multiple circles. And that's why we have pi, we could just take out, and then we have the integral of basically the change in our radius. And that's why we're doing it in respect to x, right? We're doing it in respect to x because we're revolving around the x-axis. So this only applies to a simple equation for revolving around the x-axis. Later on in the video, I'll explain how to do it revolving around the y-axis and for more complicated functions, just not like this. Okay, so that's the general idea of how this equation works. It's not a new equation. It's basically just a thinking of a old equation and then just applying it, which is how calculus works. So let's actually try like an example. Let's say we have f of x. Let's do something a little bit like hard, but not really that hard. Let's say x squared, right? X squared, a parabola. So we have a parabola right here. Actually, let's draw this a little bit better. Alright, so something like this, right? And let's say we want to get it from x is equal to 1 to x is equal to 3. And now, basically, we just need to follow the formula. So we have volume. Let's actually write it a little bit over. So our volume is equal to pi times the integral. So our integral, a is our beginning value and b is our final value. So we have from 1 to 3. Okay? From x is equal to 1 to x is equal to 3. I don't know why I'm having such a hard time writing 3. Okay? So let's draw that on the graph. So we have 1 is right here and 3 is somewhere around here. And we have this area, okay? And we want to revolve. Let's use a different color actually for the area. So we want to use this area right here, right? And we want to revolve this this area around the x-axis, okay? So we want to revolve it around here, okay? Looks a little weird. Let's actually just move it a little bit over. Okay, so you want to revolve it around the x-axis. So we have some kind of shape, and then we want to revolve it around, so it looks something like this, right? And we just need to color it in, right? So we look something like this, basically, and it's filled in the middle also, basically. So we have that as our general shape if we kind of revolve this area around. So what would that what would that area be? Well, now we just need to continue on with the formula. So it goes from 1 to 3. Our f of x is x squared. And then we have to square it. And then respect to dx. Okay. So our volume is equal to pi times the integral from 3 to 1. 1 to 3. X squared. So that's x to the power of 4 dx. So what's the integral of x to the power of 4? Well, the integral is basically just 1 over 5 times x to the power of 5, right? Because the derivative of this is just 5 times 1 over 5, which is just 1. And then 1 minus the 5 is just 4. So our derivative of this equation is x to the power of 4, which is what this is. So that is our equation. So this equation, we want to get from 1 to 3. Okay? So now we just need to plug it in. So what's 3 to the power of 5? Using our calculator, 3 to the power of 5 is equal to 243. And then we multiply by 1 over 5. So that's 243 divided by 5. Minus, now we have to plug in 1. So 1 to the power of 5 is just 1. 1 times 1 over 5 is just 1 over 5. So that volume is just 242 divided by 5, right? Well, that's just for this section. We still need to multiply by pi. So whatever you have, just multiply by pi. So your answer is actually just 242 divided by 5 pi. Is multiplied by pi. Technically, in calculus, you sometimes don't really need to simplify, so you don't have to multiply 242 divided by 5 times 3.1415, etc. You can just leave it as 242 pi divided by 5. And that's technically your answer, the most precise answer. So that would be the volume for this area if you were to revolve it around the x-axis. And that's the general idea of how to do it. It's basically just that simple. Okay? Now, that was just revolving around the x-axis. Now, how do we revolve it around the y-axis? Well, it's just a slight modification around the equation. It's still the same equation, but what it is that instead of making it in respect to x, we're gonna now make it in respect to y. So what we do is that we have v pi times your integral. It's the same equation basically, but now it's gonna be y from a to y of b. So now we're not gonna do it in x, now we're gonna do it in y. So we have f of y. Now that f of y is squared times dy of dy in respect to y. Right? So the only thing I changed is that now it's not x, and all the x's are changed to y's basically. Because now we're doing respect to y, and since we're doing respect to y, we had to go from domain restriction of y. And we just have f of y now instead of f of x. So basically, we just need to put the equation in terms of y, in terms of x, in terms of y basically. So how would that look? Well, let's use our same example again with a parabola. So let's say something like this. Actually, let's not draw that arrow. Okay, and let's say we want to find the area from here to here, right? That is our area that we want to find. Use a different color. So this is the area we want to find. And we're going to revolve this area around the y-axis. So it's going to go this way around the y-axis, right? 360 around. So our general shape will be something like a circle on top. Then it kind of looks like almost a bowl. So it kind of looks something like this. Right, and on the bottom, like a circle. Now you just color it in basically. Right? It's since you're looking like at this perspective, like you're looking towards it, you're not gonna see the circle on the bottom. But it's basically kind of like a bowl, but like an empty bottom basically, if you revolve it around. It's always good to draw a picture to understand how it looks like visually. But if you don't, it's not mandatory, but it's good. It's good. But so we have y is equal to x squared. So the first thing we want to do is that we want to put it where we just need to isolate x, because now we need to do it in y, right? So all you have to do is just square root both sides. So square root y, square root x squared. Square x squared is just x, right? Now we have it in terms of y, so we're good. So basically, all we have to do is volume is equal to pi times, okay, we need to do a domain restriction first, actually. So where do we want to put our domain restriction? Let's say we want to restrict it from x is equal to 1 and x is equal to 3 again, right? But now we're not supposed to do that. We're supposed to put y is equal to something. Well, basically, all we need to do is just put it in our equation. So if x is equal to 1, what is y? Well, y is equal to 1, right? Because it's just x squared. Now, x is equal to 3. 3 squared is 9, right? So we have y is equal to 1, and, oops, sorry. And this is y is equal to 9. So we have the integral oops, okay, times the integral from y is equal to 1 to y is equal to 9 of your equation. So our equation is square root y squared dy. Okay? So we just need to do an extra step, basically. We just need to rewrite it in a different equation. And an additional step where we have to find what the y's are if they didn't give it to you. So why do we have the 1 and the 9 for our y is equal to 1 and y equals 9? Well, technically, our y value is equal to 1, right? Because if our y value is equal to 1, what's our x value? Our x value is 1. Now, y is equal to 9, our x value is 3. Because if you think about it, our radius is now not the height, right? Because before we had the height as our radius. Our height now is our length. So these are our radius, right? Because we're revolving around around the y-axis, right? So this would become our new circle, right? If we have to draw a circle with these lines, because we're revolving around the y. So technically, our lines here are gonna become our new radius, and that's why we have to whatever we plug in for a y, then our x that outputs will basically become our new radius, and that's the reason why we do this. So we have volume is equal to pi times. Now we just need a integral 901. Now we just need a square. So we'll square y times square y squared is just y by itself, dy. So what is the integral of y? Well, it's just 1/2 y squared, right? Because the derivative of 1/2 y squared is basically just 1/2 times 2, which is 1, and then 2 minus 1 is 1, right? So it's just y to the power 1. So the derivative of 1/2 y squared is just y. So this is true. So our equation, 1/2 y squared, and we're going from 9 to 1. Okay, so we just need to find the measurements for this. So what's 9 squared? That's 81. 81 divided by 2, right? Because we need to multiply by that half. Minus, now 1 squared is just 1. And then 1/2 times 1 is 1/2. So 80 minus 81 over 2 minus 1 over 2 is just 80 over 2. 80 over 2 is just 40. Now we just need to multiply by the pi, right? Because this section is just all 40. Now we just need to multiply by pi to get the answer. So we multiply by pi, and that is all. So the volume of our restriction from y is equal to x squared, from x is equal to 1 to x is equal to 3. And if we revolve it around the y-axis, right, this picture is basically equal to 40 pi. And that is our volume. The area and the volume are not going to be the same. If you kind of understand that. It's basically because, well, generally volume and area is not supposed to be the same. Sometimes it could be, but not all the time. So this calculation we made is our volume, which is what we're calculating for, not the area. If you want the area, that's basically just the integral. Okay. Now that was just for the simpler cases, for respect to x and respect to y. For the rest of these cases, we're just gonna do it in respect to x, because if you want to do it with respect to y, you just need to change all the x's to y's and basically just reverse the formulas. Okay. So, but for those past two examples, they were only for simple cases where we have like a graph and we have like a line. So let's do some kind of like line. Just gonna do a linear line because it's easier. And we had to find an area under this, right? So that was just a simple case. Now, what happens if we have like an actual hard case, like an actual case where we have like multiple equations? So let's say we have an equation like this, and we have an equation like this, right? And they have these area that's restricted right here, right? Now, if we were to revolve this area around the x-axis, what would be our volume? So it's a lot harder. Well, a little bit harder. The general idea is that instead of using one circles, we're going to be using two. So how this looks like is, let's have like, let's actually use two colors. So we're going to use red for our top, and we're going to use blue for our bottom. Okay. So let's first make our lines for our top. So we have since it's restricted right here, we're only gonna make points between it. So let's say a line here, and a line here. Okay. Usually I like to do 3 lines. And then we're gonna from here we just overlap, right? Because it's the same point, same line. So it's like here, here, and here, right? It's the behind the blue line is the red line. Don't forget that. So basically, what we could do is that we're gonna make a circle for the red first, and then we're gonna make another circle for that one. And we're gonna make another circle for that one, right? So that's how it looks. We're just gonna use one circle since it's actually really hard to see. So let's just use the smallest one right here, right? So we're gonna make a circle around that one, and then we're gonna have a circle. That circle might be a little bit too big. Okay, that's fine. And now let's make a circle for the smaller one, like right around here, right? So basically, what we're gonna do now is that we see an area for the circle, right? It's this entire area. But now that area, we have a blue in there, right? We have this area of blue, this circle area of blue. So how do we calculate this area? Well, it's simple, right? We have 2 circles. So let's draw this where we're actually like looking at it. So we have a circle, and we have like let's just color it in. So that's all our circle for red. And we have a circle. Oops, wrong color. And this circle area is blue, right? So it's basically just that picture. But now we're looking at it like from this perspective, right? So we're not looking at it from the screen, we're looking directly at it. So basically, this area, how do we find the area of just the red and you take away the blue? So any area that's not overlapping. So basically, it's very simple, right? The equation, the area of the first circle is just pi times whatever that radius is, squared, minus pi, right, of our small circle. And that's basically it. That's basically how this is going to become our new radius. So that's our new area. So now our formula for the volume is pi times the integral from, instead of saying, we could just say x, right? From a, and x is equal to b. So now instead of saying like just one equation on the next, we're gonna actually just put these equations by side. So the first equation, we'll call it f of x. We're gonna have f of x squared, right? Let's actually use a different color, so it'll be easier to see. So let's use red. F of x squared minus, now the blue, chi of x squared. Okay. I'm running out of space, but don't forget, you always have to do it respect to like some kind of variable. And since we're putting x's respect to dx, right? So dx is supposed to be all the way over there, but I don't have space. So this will become our new equation. And that's basically it. We just all we have to do is just that we have to add this part. We have to minus some area away. Right? Because if you keep drawing circles, right, and there's always like a other circle right here that takes it out, then basically what happens is that, okay, let's erase this. Okay. So if we have an area, we have these lines, right, and we have these lines right here for the blue, then the entire red line minus that blue line would just basically be left with the red lines inside, right? And these red lines, if you put infinite amount of them, right, then basically you just get the area of this section. And that's basically all you want. So that general idea of how it works. So instead of using like one circle, we're going to use two circles. One circle, which is the outer circle, minus the inner circle. So there is a specific purpose, and you have to put this order correctly, right? So you have a equation on top, and you have equation on the bottom. So the reason how this works is how you can set up your equation is that whatever equation is on the top, actually I should use a different color. Let's actually use white for our graph again. Okay, so let's say red is the equation on top. Okay, right here, and blue is the equation on the bottom. Okay, whatever equation on the top, that's gotta become your first equation. Okay, so whatever equation on the top, that's gotta become your f of x. Whatever equation on the bottom, that's gotta become your g of x. Because it's f of x squared minus g of x squared, right? So which one are you supposed to subtract away from? Well, you have a radius up here and you have a radius down here, right? Well, you're supposed to subtract the bigger radius by the smaller radius. And that's why we put the g of x, the bottom one, the bottom equation as g of x. Because then we just subtract that one away. So you have to think about this intuitively. So that's just for respect to x. Now, what will we do when we want to do respect to y? Well, basically, whatever is the outer boundary is going to become your first equation. So this is for y. So since your line is like right here, right? You're doing respect to y. Then your x is like right here, right? So you're supposed. So now you have your blue subtracted by your red, right? So technically, whatever is in your outer boundary, which is usually the right one, the one that's most right, then basically that equation is going to become your f of x. So this equation has become your f of x, and this equation becomes your g of x, right? Because your equation is always just f of x squared minus g of x squared, right? It's based on the formula I just gave you. Then you're supposed to have the bigger radius minus the smaller radius. So that's all you have to think about. Which one is the bigger one and which is the smaller one? And you subtract them one away. Sometimes it might be a little bit weird, like if you don't like the question is not asking to revolve around the axes. So let's say they want to ask you to revolve around the line right here, right? So if you want to revolve around this line, then basically your outside equation is now your red. So your red here is now f of x. And your g here is now g of x. Your blue is now g of x. So why would that be? Because since you're revolving around this line, right, that means you're making circles like where your radius is right here. And then your blue, your g of x, has to be right here, right? So you have to subtract. So the red has to subtract away from the blue. So it's more about like logical thinking. It's not usually the right most, but sometimes it is when you have to do revolutions, basically for subtracting. So what you have to think about is you have to think logically which one is the bigger radius and which one's the smaller one. Or more intuitively, you have to think about which one's your outer boundary and which one's your inner boundary. So f of x is our outer boundary and g of x are our inner boundary. So you have to subtract your outer boundary by your inner boundary, and that's basically how you do it. So it's just a little bit more difficult, but once you get pretty good at it, um, you would do this like pretty easily. So generally, if you want to do these kind of formulas where it's really difficult, sometimes then you might want to use the calculator or like draw it by hand. Usually, I like to just draw it by hand. So let's try an example with this. So let's say our volume is equal pi, right? So I gave you the formula already. So x is equal to a, x is equal to b. So this x tells us we have to do respect to x, right? So for these examples right now, we're just going to do respect to x. If you want to do it respect to y, it's basically the same idea. It's basically just volume is equal to pi times the integral from y is equal to a to y is equal to b, and then fy squared minus g of y squared dy, right? Basically the same thing, right? I forgot the parentheses right there. So you're supposed to square the equations. So that's basically all you have to do. You just need to change the x and y's, and now, like how we did it for our simple equation, where we just reverse our equation, like y is equal to x squared to square root y is equal to x, right? You have to do that for y's. Whenever you do respect to y, you gotta reverse your equation, so you can isolate the x. Once you do more of this, you start seeing what you need to do intuitively, right? So let's try an example. We have an equation, we have a graph, right? And let's say we have equation up here, and we have a equation down here. Okay. So let's try like a simple case for this, right? So we just want to find this area in between them, and we want to revolve it around the x-axis. So our top equation, we're going to say that's y is equal to square root of x. Oops. Square root x. And the equation on the bottom, we have y is, actually, we have it as, let's say, g. G is equal to x. Sorry about that. I don't know if I got right. Is equal to x squared. Okay. So now let's actually just put it in this formula. So volume is equal to pi times your integral. So let's restrict it. Usually, when we have these equations where there's multiple equations, you already have the domain restrictions. What they want to do is that they want to find the area bounded, right? So when would these intersect? So let's actually solve for when they intersect first. So we have square root x is equal to x squared, okay? Right? Because y has to equal to g. So when would these intersect? Well, let's just square both sides. So square root x squared is just x. X squared squared is just x to the power 4, right? Now 0 is equal to x4 minus x. So 0 is equal to x cubed minus 1. So x is equal to 0 and x is equal to 1. Okay, so those are our points. Okay, so our points is that x is equal to 0, which is obvious because they both go through the origin. So they go through the point 0, 0. right? Because if you put 0 here, then that's 0. Put 0 here, that's 0, okay? And they also go through 1. So square root 1 is 1, right? So they both go through a point 1, 1, right? Which makes sense. Okay? So this is 0, 0, and this is 1, 1. Okay? And now we want to find the volume between it. So our volume is equal to pi times our integral from 0 to 1, right? Because our x is 0 and x is 1. Now, as fx squared, so our fx is our outer radius, right? So we're revolving around the x-axis. So which one is the bigger radius? So our our red is our bigger radius, right? Because you have to draw like line down here because we're revolving around the x. And our blue is right here on the bottom, right? So these are our blue, right? So we have to revolve. So the blue is our lower bound, and our inner bound, and our red is our outer bound. So because we're around the x, so you have to. That's why we have to draw a picture sometimes, so we understand how it looks. So now we have the red minus our blue. So our red is f of x. So square root x squared is just x minus g of x. G of x is our g right here, so x squared. So x squared is x to the power 4. Right? And then put parentheses around there, and then write dx. Okay. So what's the integral of that? The integral. Okay, let's actually set it up first. So we have 0 and 1. So the integral of x is x to the power of 2. And then we have 1/2, right? So 2 times 1/2 is 1. Minus 2 here is x. So the derivative is x. Okay, so that makes sense. And this is 1 over 5, x to the power of 5. And you can add a C if you want. I usually don't because then it kind of wastes time. But it's good practice to do. But for this case, we're just not going to. It's not going to change your calculation at all anyways, because you're going to plus C and then you're going to minus that C away, so it just doesn't do anything. Now, if we have x is equal to 1, we have 1/2 minus 1 over 5. So 1/2 minus 1 over 5. That's just 5 over 10 minus 2 over 10, so that's just 3 over 10. Okay. So we have 3 over 10 minus 1 is x is equal to 0. So that's just 0 minus 0. So that's just 0, right? So 310 minus 0 is just 310. Okay. So this portion right here is just 3 over 10. Okay. And then now we just need to multiply by pi to get the answer. So 3 over 10 pi, 3 over 10 times pi is our volume. And it's basically just that simple. We just now have an outer radius, the area of the outer radius minus the area of the inner radius, right? The area of the circle of the inner radius, and then inner area of the outer circle, and then the area of that minus the inner radius and the area of that, and then you subtract them, and then you do an integral, and then multiply by pi. And that's basically all you have to do. And that's for when you want to have multiple equations restricted by that, by 2 lines, and you want to find the area between. Okay. So let's now actually try to do a revolution that's not actually with the x-axis or the y-axis. One where we have to like do it parallel to a graph, like to one of the axes. So how would that look? So let's say we have an equation. Let's just use our equation again, but now let's have something right here, right, and right here. So we have this area, but now instead of revolving around the x-axis, let's say we want to revolve it around, let's make this a dotted line, around a line right here, right? So what would that look like? Well, it's going to be really, really hard to draw, but let's kind of have something like this, and then something like this, right? So it's just this shape. Now we have to make it 3D. So it's around this line right here. So it kind of looks like circle, another circle, kind of like the same shape right here, right? And then you kind of color it in. So it kind of looks like something like that, right? But then there's like something with inner, right? So you have like inner in here. So it kind of looks like a wheel-ish. But I have a really bad drawing, so it's supposed to be look like really weird inside, and then kind of gets like smaller outside, and that's what it looks like. Right, so that's basically what it looks like. It kind of looks like a wheel, but it's a little weird. So it's really hard to draw it in 3D, but that's basically what it looks like. So what we do, well, instead of thinking it as like one of a line, we're gonna move it up. So our original graph looks like this, right? We're just gonna move this equation up, and then basically now we're gonna have um. Let's actually use a different color so we see how this looks. So we have this red line, right? And now we're gonna have this red line on the x-axis. So it's gotta be exactly on it. So where would this graph be? Well, it's gotta be on top now, right? So it looks like something like this. And now you could basically just do it a revolution around the x. And that's basically all it is. You just move the equation up. It's just gotta be the exact same volume, but now you just gotta look at it in a different way, right? It's gonna be the same thing no matter what if you move the volume up or down. So this is the same thing. And that's basically it. So how would that translate into a graph? Well, let's say our outer boundary is f of x, right? That's our outer one. Well, now it's not at f of x, right? It's at f of x plus wherever your line is that you want to rotate around, right? Because our original equation, f of x, let's say it looks like something like this. Well, instead of it being right here, now it's going to be higher. Like we want to do it in relation to a point, like a line right here. Well, instead of that, if we move this up to right here, right, and this is right here, then you have to move this up by the same amount. So it's going to be somewhere up here, right? So this is f of x plus a, and this is f of x. And that's basically all you have to do. You just have to add an a in there. So what would that look like in our volume formula? Well, all you have to do now, you just have to, instead of writing f of x, you have f of x plus a. But in this case, we're just going to use h because that's for height. So we have pi times the integral from x is equal to a to x is equal to b. And we have, let's use red. And we have f of x plus h, right? Because now it's not f of x anymore. We have to replace it with f of x plus h. And we're going to have that squared. And we're going to minus by g of x plus h also. Because this one's also getting scaled up. And then you're going to do this all in respect to dx. Okay? So this has become our new formula. And it's basically just that simple. All these formulas is just slight modifications so we can fit their scenario. That looks weird as a 2. Let me delete that so we can actually get like 2 out here. Right. So 2. Okay. So let's draw an example. So let's say we want to do it at y is equal to, I don't know, -2 or something, right? And let's use the exact same equations on the top and the bottom that we used in our previous example. So we have this, we have our square root function, and we have our quadratic function, right? And we want to have an area, and this area is revolved around y is equal to -2, right? So it's around here, this entire area. So what's the volume of that shape? Well, basically, let's write our equation first. Y is equal to square root x, and y, our g is equal to x squared, right? And the points where that they crossed is still the same, right? Is at 0, 0, and is at 1, 1. Okay? Oops. 1, 1. So now let's actually do the math on this. So our volume is equal to, let's actually write this closer and a little bit smaller, pi times the integral from x is 0 to x is 1, right? And we have f of x plus h squared. So write that in red. So square root x plus, so we had to move this up 2, right? So we had to get from -2 to 0, right? Till we get to the x-axis. So we have to add 2. So we just need to add 2 squared. And then we have to minus by our inner boundary now, right? So we have x squared. So this is also getting up by 2, right? Because if this is going up by 2, then this is also going up by 2 squared. So basically just follow the formula. And then in respect to dx, which I'm running out of space on. Okay. So now we just need to simplify this equation. So our volume is equal to pi times our integral from 1 to 0 to 1. So this squared is square x squared is just x plus 2 square root x plus 4. And then we have to minus x squared, so that's minus x to the power of 4. I'm running a space, so I'm going to put it on below. So that's plus 2x squared, so that's 4x squared, so that's minus 4x squared. And that's plus 4 minus 4, right? So what can we cancel out? We can cancel out this plus 4 and this minus 4, right? Because if you add them together, they're just going to be 0. So we cancel those out. And do we have anything else? And no. Right, so our volume is equal to pi times our integral from 0 to 1. And our equation is, let's put it from biggest polynomial to smallest, right? So we have negative x to the power of 4. And we have an x squared. So we have minus 4x squared. And we have an x. And we have a 2 square x. Oops, running out of space. Let's kind of move this over so we actually get some room. Okay, that's fine. So we put it somewhere here. And plus 2 square root x. And respect to dx. Okay. So if you want to copy this formula down, I need to move it up so we get a little bit more room to do the math here. Okay. And now we just need to follow the formula to get the answer. So what's the integral of this? It's 1 over 5. X to the power of 5, right? Minus, this is x to the power of 3, so this is 4 over 3. X to the power of 3. This is plus x, so this is 1/2 x to the power of 2. And this is 2 square root 2 square x. So this is supposed to be, this 1/2 is x to the power of 1 over 2. So this is x to the power of 1 over 3. So plus x to the power of 3 over 2, right? Because 3 over 2 minus 1 is just 1/2. So that's just square root x. So this is 3 over 2, but I need a 2 in front. So I need to have 4 over 3. Okay? So this is our equation. And now we just need to plug in x is equal to 1 and 0. 0 and 1. So we don't have, if we put 0 in here, that's just -0 minus 0 plus 0 plus 0, right? So technically we won't have to do the 0 part. So we just need to put in the 1. So if we put 1 here, that's just -1 over 5, -1 over 5. minus 4 over 3 plus 1/2 plus 4 over 3. So what can we cancel out? Well, we could cancel out this part, and we could cancel out this part, right? So the area is just 1. I mean, the volume is just 1/2 minus 1 over 5. That's just 3/10, right? So 3/10 times our pi. And that is our volume. 3 pi tenths. And that's basically all we had to do. Okay. So that was basically all the general idea of how to do volumes from revolutions. However, there is additional aspects about volumes that aren't about revolutions. So the general idea is now that instead of doing circles, we're gonna do like actual shapes. So for like an actual shape. So what it is like let's say we have a line, right? Let's just have 2 lines so it'll be easier to understand, right? So this is just a specific case. I'm trying to do a general case. So the idea is like we have our outer boundary minus our inner boundary, right? So this line, then minus this line, right? So we just get the area inside. So all the area inside here, basically. So let's just restrict it like somewhere right here. No, that's fine, right? So basically, what we want to do is that all this length, we want it to be a specific shape making it 3D. So imagine we have this as our imagine this is like our like if you have a 3D like shape, right? Let's say we have a cube, right? So we have something like this, right? Imagine this is our this is our bottom face, right? So imagine this area is our bottom face. Okay? So what we want to do now is that based on this area, we want to make a specific shape, right? So imagine we want to that every single line of here is supposed to make a square, right? So if we draw a line here, and then 3D wise, right, it's gonna make a square. And then like another line makes a square. Another line makes a square. It might be really, really hard to visualize because we're looking at it in 2D, trying to draw a 3D image. But basically, like like as I said before, this is gonna be our face, so it's gonna be on the bottom, and we're supposed to draw something that's like sticking out. So it's like going towards like a z-axis, you know. So we're trying to draw a square. So this is our line. We want to draw a square. Really hard. Let's actually just use the smaller side. So this, and we draw a square. Then something like right here, draw a bigger square. Then something like right here, draw a bigger square. Right? Now, if you add all these squares up together, right, then basically what we have is that we have some kind of shape. It looks like this. And then, oops. And then we have a height. That's a square. And that's like this. And we have something like this, right? And then we have basically a prism, right? So if you think about it, we just have some kind of like, well, it's not really a prism. It's gonna be like some kind of like shape thing. So it's gonna like scale up. Looks something like this. It's gonna scale up, right? So it's like a little. It's kind of like a prism, but like the cut is like on the top is a little cut off. So the general idea is that it's just gonna be a prism, right? So instead of like making circles now, like we're revolving around something, these lengths are now gonna become our new like length, and these lengths are gonna help us like determine some kind of sort of height. So the general idea is that it also follows a specific formula, like all these other ones do. Basically, the idea is the volume is now equal to the square root of the area, and wherever your domain restrictions are, basically, and then in respect to dx, right? Or dy, depending on where you want to use, right? So that also applied to our circle formula, right? Which is just pi radius squared, right? We wanted to do a, when we were using circles, we did an integral of that. And the reason we put the pi on away from the integral is because since pi is a constant, we just move it out. So that's just a basic property of integrals. So the when we were working with revolutions, which we were using circles, they were actually doing the exact same thing that we are using now. This is just a more general case. So this is just an integral of an area, basically. So basically, all we have to do now is that we have to put this in like some. So since this is a general case, if we had to use like a specific example to like actually show how this works. So I put a line under here. So let's say we want to have a graph. Let's say y is equal to, let's do our scenario that we drew out. We have a line here and we have a line here. Let's make this easy and say this y is equal to 2x and say this y is equal to x, right? And the distance, right, between the lines, each of those distance is gonna be a length of a square, okay? So imagine we had to make a 3D shape on the bottom, right? And then we had to make a like square heights of those shapes. So what would be our height? Well, our height would just, since it's a square, right? Our length is just gonna be equal to our height, right? So basically, all we had to do is that our height is now equal to whatever our length is. And to find the area of that, it's just our height times our length, right? And since our height is equal to our length, it's just length squared. So whatever we have as our length, we just square it. So what is our outer boundary? Well, our outer boundary is 2x, right? And our inner boundary is x. So now we just need to write our integral. So our volume is equal to pi. Not pi, equal to our integral. So our outer boundary, which is 2x, minus our x, right? So 2x, the height here, minus our x, so this height right here, basically, will get us our, just this line, right? So that's the general idea. So the integral would do all those lines between. And we need to do a domain restriction. So let's say x is from 0 to x is equal to 1, right? So let's do like a really simple case. So 0 and 1, right? And since this is the area, right? We said that this length is going to be our length, and our height is equal to our length, right? Because it's a square, because we want to make these into squares. So we had to square it, right? Because our area, this is our length. Length squared is equal to our area, right? Because the length is just a side of a square, right? Times d of x, or just d of x, basically. So what is this squared? Well, basically we just have 4x squared minus, actually, let's subtract these first. So 2x minus x, that's just x. So that's just x squared. Okay, so it's basically just that simple. So the integral of x squared is just equal to 1/2 x squared, right? Oops, sorry. Is equal to 1/3 x to the power of 3. And it goes from 0 to 1. 0 to 1. So putting 1 here, that's 1/3. Putting 0 here, that's 0. So 1/3 minus 0 is just 1/3. So the volume of our shape from 0 to 1, right? And you have to do it like with cube, with squares, is 1/3. And that's basically it. So if you still don't understand, we'll try like another example, but instead of using squares, let's use something like a triangle, right? So let's use this case. So let's say the base, whatever the thing is our base, our triangle let's say its height is 2 times its base. It's 2 times the length of its base. Okay? So how we find the volume? So basically, let's find out what is the general area for this triangle. So the area for a triangle is length times height divided times 1/2, right? Or divide by 2, same thing, right? So our height is 2 times the length, right? So that's 2L squared times 1/2. So it's equal to L squared. Okay? So we just need to put in whatever our length is, we just need to square it. Actually, let's do a different case. Let's say the height is 3 times its length. So we have H times L times 1/2. I just don't want to use the same number that would like simplify it to make it look like a square when it's not. When it technically was, but I'm trying to make a example that makes more sense. So we put an H in here, so we have 3 divided by 2 L squared. Okay, so this is our formula that we need to use. So 3 squared 3 divided by 2 L squared. Okay, so our volume is equal to the integral of 3 over 2. So what's our L? So our L is basically just that difference, right? So it's 2x minus x. Then we square it, and then dx, right? Because our length is squared, our length is 2x minus x. So now we just move 3 over 2 to the outside, and then just do an integral of this. So our integral x squared dx. And let's use our same domain restriction from 0 to 1, right? So we already did this part in our previous example, and we got it was equal to 1/3, right? So 1/3 times 3 over 2, because we have this 3 over 2 up here. So 1/3 times 3 over 2 is 1/2. So the volume of the shape where bounded by the graph y is equal to 2x, outside and inside is y equals x. And that difference, which would make a length, that length, which will make a triangle that has 3 times its height, that volume of that shape would be 1 over 2. And if they have units, like just put what the units are. Like if it was inches, then it's inches cubed or something. And that basically like summarizes everything for integral volumes. Thanks for watching, and I'll see you at the next math record.